In the previous lecture, we have discussed the design of welded joints for direct loading. In this lecture, we are going to discuss the design of welded joints for eccentric loading. There are two cases of eccentric loadings are there. First one is out of plane eccentricity and the second one is in plane eccentricity. So first I'll tell you the difference between out of plane eccentricity and in plane eccentricity. In the case of out of plane eccentricity, the welding and the loading is acting on a different plane. So they are not acting on same plane. In the case of in plane eccentricity, the welding and the load is acting on the same plane. Okay, so that is the difference between out of plane eccentricity and in plane eccentricity. So here this is the example problem for out of plane eccentricity. So here the welding is carried out at this plane and the load is acting here. Okay, so they are acting at different planes with some eccentricity. Okay, so that is why it is considered as out of plane eccentricity. Okay, so here in this problem the welding is carried out here and the loading is acting here. So both are in same plane, that is the welding and the load is acting on the same plane. That is why it is considered as in plane eccentricity. Okay, so first you have to identify the case whether it is out of plane eccentricity or in plane eccentricity. Then based on the case we can do the design procedure and we can calculate the weld size. So first consider out of plane eccentricity. So we know that when the load is acting with some eccentricity, we have to consider two stresses. The first one is direct stress and the second one is secondary stress, or primary stress and secondary stress. So in primary stress, we will just neglect the eccentricity and we will assume that the load is directly acting on the plane. Okay, so if it is primary stress, then assume that the load is directly acting here. There is no eccentricity, so here actually the eccentricity is here. So this is the E value. Imagine that the load is directly acting here. Okay, so if the load is directly acting here, then what will happen is it will produce a direct shear. Okay, so if the load is directly acting here, then it will produce a direct shear. Okay, and we know the equation for direct shear, that is tau is equal to load by area. It is P divided by A. So here P is the load acting and A is the area of weld. So remember that in primary stress we have to neglect the eccentricity. Then the secondary one is with considering eccentricity. So here the eccentricity E should be considered. Okay, so if the load is acting with some eccentricity, then what will happen is this eccentricity will try to bend the weld. Okay, so actually it will bend like this. So if you see this image, then it will try to bend the welding like this. Okay, so it is producing some bending stress, and we know that the bending stress equation is sigma B is equal to M by Z. Okay, so primary stress, the load is directly acting here. So if the load is directly acting here, then we will get a relative loads in the opposite direction and this will produce a shear stress. Okay, that is primary stress. And in the case of secondary stress, the eccentricity should be considered, and this eccentricity will produce a bending, that is it will try to bend the weld like this. So the bending stress is produced. Okay, so the loading is here and the load is the welding is here, the load is acting like this, so it will try to bend the weld like this. Okay, that is why it is producing bending stress. So the primary stress is tau and the secondary stress is sigma B. So we have to calculate the maximum normal stress and maximum shear stress. Okay, so here it is a combination of normal and shear stress. So we can use the principal stress equation to find out the maximum normal stress and maximum shear stress. So sigma max is equal to half sigma B plus root of sigma B square plus 4 tau square. So here sigma B is the bending. So this sigma max and tau max equations we have already studied in CO1, that is combined stresses. So it is same. So sigma B is bending, tau is the direct shear. Then in the case of tau max, sigma b is the bending load, then tau is the direct shear. So here sigma b is equal to m by z and m is the bending moment. Okay. So here it is like a cantilever beam, and we know that for a cantilever beam, the bending moment m is equal to load into eccentricity. So load into perpendicular distance. So here the perpendicular distance is eccentricity. So it is P into E. And Z is the section modulus. So section modulus of the welded region. So this Z equation is there in the data book page number 11.5. So I'll tell you how to select the equation from data book page number 11.5. So this is how we have to calculate the primary stress, secondary stress, finally the maximum normal stress and maximum shear stress. Okay, so this is for case 1, that is out of plane eccentricity. So remember that for case 1, the primary is shear and the secondary is bending. So it is shear plus bending. For case 1, it is shear plus bending. So we'll move into case 2. So this is again another example of case 1. So here in the previous problem, the welding is carried out in a square region. So here it is carried out in a circular region. Okay, so there is no different. The welding is there in this plane and the load is acting at a different plane. So eccentricity is there and both are acting at a different plane. So it comes under case 1, that is out of plane eccentricity. Okay, so here also it is case 1, the same shear plus bending. So here the primary stress is shear stress because we know that the load will directly act here. Okay, and in the case of secondary stress, the eccentricity will be considered. So sigma b is equal to m by z, that is bending moment divided by section modulus. So here the only difference is in the previous example, we know how to calculate the area for weld region, that is 0.707 h into L. So in the previous case, the length can be calculated from the drawing, but here the weld is carried out in a circular manner. So the length of the weld is the circumference of the circular region, that is pi into d. Okay, so the length of weld is circumference of this circular bar. So this is in the case of circular bar, but the concept is same. Okay, so direct primary stress is shear stress, secondary stress is bending stress, so that you can calculate sigma max and tau max using the principal stress equation. Okay, so this is also case 1. Then this is case 2. In plane eccentricity, the load is acting on the same plane of the weld. Okay, so you can see that it is on the same plane. Okay, fine. So first consider the primary stress, that is without considering the eccentricity. So here the welding is carried out here and the load is acting with some eccentricity. So this is E. So this is actually the right side view of this welded region. So E is the eccentricity. So if we are focusing on the primary stress, just neglect the eccentricity. Imagine that the load is directly acting here. So if the load is directly acting without any eccentricity, then it will produce a shear stress, and that is the primary shear stress, that is tau 1 is equal to P divided by A, that is load by area. Okay, so here A is the area of the weld. Okay, we know that A is equal to 0.707 H into L. So H is the weld size, L is the length of the weld. So here the weld is carried out in this region. We can calculate the length of the weld, that is 100 plus 2 times 50. Okay, so that is the length of the weld. So this is for direct shear stress. And the second one is with considering the eccentricity. So consider the eccentricity, the load is acting here. Okay, so if the load is acting here, then what will happen is it will try to rotate the plate like this. So the plate is like this. When the load is acting, then it will try to rotate the system like this. It will try to rotate the system like this, and because of this rotation, a secondary twisting moment is produced here. Okay, so if the load is acting here, then a twisting moment is produced on the welded region. Okay, so actually this plate will bend. Okay, but we are not going to calculate the stress on the plate, and because of the bending of this plate, then the plate will rotate and it will produce a twisting moment in the welded region. Okay, so that is the secondary stress and it is a twisting moment. So the equation for secondary shear stress is tau 2 is equal to T by J into R2. So here T is the torque, that is load into eccentricity. Here the load is 60 kilonewton and the eccentricity is E. So here one thing is very important. So in the welded region, we have to consider one center of gravity point. Okay. So eccentricity is the distance between the load acting and the center of gravity. So this is the center of gravity of the weld region. For example, so this is actually the weld region. Okay. Yeah. So this is like a C section and the center of gravity will be here. So eccentricity is the distance between the load acting to the center of gravity. Then this distance should be considered as R2, that is the radius from the center of gravity to the weld joint. So this is the R2. So for this case of problems, we have to calculate the position of center of gravity and from that we have to calculate the R2. Okay, so while solving the problem, I'll tell you how to calculate the R2 values and everything. Then the J is the moment of inertia, polar moment of inertia, and the J equation we can take it from page number 11.5. Okay, so just understand the concept behind case 1 and case 2. While solving the problems, we will get a clear idea about how to solve the problems. Fine. Okay, so here in the case 2, the primary stress is shear and the secondary stress is also shear. So the maximum shear stress can be calculated by using this equation, that is tau max is equal to root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. Okay, so by using this equation we can calculate the maximum shear stress acting on the weld region. Okay, so this is case 2. So now I am going to solve a problem on case 1. Before that, this is the formula page for Z and J. Okay, so we have to select the Z and J equation based on the weld region. So here the weld is actually a straight line. So this is the Z equation and this is the J equation. And remember that with all the formulas you have to multiply 0.707 H. So that is very, very important. We have to multiply 0.707 H with all the equations. Okay, fine. So this is an example I have considered. So here you can see that the weld is carried out as 2 lines. Okay, so you can refer the data book. So here the 2 lines are in vertical direction, and here you can see that the welding is carried out in 2 lines and it is horizontal. So the Z equation for this region is BD into 0.707 H, and the J equation is B square plus 3 BD square divided by 6 into 0.707 H. So the next example, so here the welding is carried out in all the sides. So the welding is almost like a rectangle. So you can refer the image in the data book. So here the welding is carried out in all the directions. So this is B and this is D. So for this problem, the B is 100 and D is 150. Okay. So the Z equation is BD plus D square by 3 into 0.707 H. Then the J equation is B plus D the whole square by 6 into 0.707 H. So we have to select the formula based on the weld region, and you have to compare the given problem with the weld region given in the data book, and these equations are there in data book page number 11.5 and 11.6. So I have given you the scanned copy of PSG data book, so you can refer that. So we'll start with the problem on case 1. So the problem is a rectangular cross section bar is welded to a support by means of fillet welds as shown in figure. So this is the side view and this is the front view. Okay, so the weld is carried out in this plane and the load is acting on a different plane. Okay, so it is not on the same plane, it is on different plane, so it comes under case 1. That is, the primary stress is shear and the secondary stress is bending. Determine the size of the welds if the permissible shear stress in the weld is limited to 75 megapascal. So the P is given and the tau value is given. We have to find the size of the weld, that is H. Okay. So if you see the three-dimensional of this problem, then it will be like this. So this is actually the three-dimensional view of the given problem. Okay. So the welding is carried out in one plane and the load is acting on another plane. Okay. So it comes under case 1, that is the primary load is shear and the secondary one is bending. So first consider the primary stress, that is direct shear stress, and we know that the equation is tau is equal to load by area. So the load is 25 kilonewton, that is 25 into 10 power 3 Newton. We have to calculate the area. We know that the equation for area is 0.707 H into L. Here the L is the length of the weld. So this is very, very important. Be careful about it. We have to calculate the length based on the given drawing. Okay. So here the welding is carried out in all the sides. So the length is 150 plus 100 plus 150 plus 100. Okay. So it is 2 times 100 plus 150. Okay. So the overall length of the weld, so you start from here, it is 150, then 100, then 150, then 100. So 2 times 100 plus 150, this is the area. So you can substitute that in the equation P and A. I have substituted it. So finally if you solve this, you will get tau is equal to 70.72 divided by H. H is the weld size. We have to calculate the weld size. So you will get the tau value and sigma value in terms of H. So this is the primary stress. So here calculation of area is very, very important. So for example, if the welding is carried out like this, then you can add 150 plus 150. But here the welding is a complete square one. So it is 150 plus 100 plus 150 and plus 100. Okay. So that is very important. Then the secondary stress in the case of case 1 is bending stress. That is sigma B is equal to M by Z. M is equal to load into eccentricity. That is load into perpendicular distance, we will get the bending moment. So here in the problem, the load is 25 into 10 power 3 and eccentricity. So you can see that, so this is plane 1 and this is plane 2 and this is the eccentricity. So eccentricity is 500 mm. So 25 into 10 power 3 into 500 mm. So eccentricity is actually the perpendicular distance between the weld region and the load acting. So be clear about it. So finally you will get M is equal to 125 into 10 power 5 Newton mm. Now we have to calculate the Z value. Z, for selecting the Z equation, go to data book page number 11.6. So here the welding is a square one. You can refer the drawing from the data book. So here it is a square region. So X direction is B and Y direction is D. And in our problem, the B is 100. So you can compare the two images that is given in the problem and the image from your data book. And D is 150. So the Z equation is BD plus D square divided by 3, and I have told you to multiply 0.707 H with this. So this is the Z equation. So substitute the value of B and D. So B is 100, that is given in the problem, and D is 150. So you will get 15,907.5 H mm cube. Okay. Now you can substitute the calculated M value and Z value in the sigma B equation, so that you will get sigma B is equal to 785.8 divided by H. So in the problem, they have given the maximum shear stress equation. So we don't need to calculate the sigma max. So we can directly calculate the tau max, and tau max is equal to half root of sigma B square plus 4 tau square. Okay. So sigma B value we have calculated, that is 785.8 divided by H the whole square, and the tau value is 70.72 divided by H the whole square. So you can commonly take the H outside, so that you will get tau max is equal to 399.2 divided by h, and that is equal to 75. That is the material property. It is given in the problem. So by solving this, you can calculate the h value. That is weld size is equal to 5.32 mm. Okay, so first identify the case, whether it comes under case 1 or case 2. So if it is case 1, then the primary stress is shear and the secondary stress is bending. So consider the primary stress, tau is equal to load by area. Area we have to calculate, and while calculating the area, be clear about the length of the weld. Then after calculating the primary stress, the secondary one is sigma b, that is bending stress, that is m by z. Calculate m separately, and from the equation given in data book page number, use the equation for z and calculate the z separately and substitute everything. Finally substitute everything in the sigma max equation, because they have given the maximum stress value. So if sigma max is given in the problem, then you can use the sigma max equation. So here in the problem, tau max is given. That is why I have calculated the tau max value. So substitute everything and calculate the size of the weld. Okay, so this is the weld is calculation of weld size for eccentric loading comes under case 1. So this is the tutorial problem. A bar of rectangular cross section is welded to a support by means of fillet welds as shown in figure. Determine the size of the welds h if the permissible shear stress in the weld is limited to 70 megapascal. So tau is given, we have to calculate the h value. So this is the given drawing. So again it comes under case 1. So this is the weld region, this is plane number 1, and the load is acting on a different plane. Okay, so the P is 45 kilonewton, E is 500 mm, and here also the welding is carried out in all the sides. So the outline of weld will be a square line. Okay, so there is almost the problem is like the classwork problem. So it comes under case 1. So primary stress is shear and secondary stress is bending. Okay, so you can refer the classwork problem and you can solve the tutorial. So the final answer, the size of the weld h is equal to 10.3 mm.